All right, let's just dive right into this. Every single time you open your eyes, your brain performs what is basically a mathematical miracle. I mean, you look out into the world and you experience this rich, immersive, three-dimensional reality. But the actual light hitting the back of your eye, it is completely 100% flat. Your retinas are essentially just two-dimensional canvases, capturing nothing more than a flat projection of light and color. So how exactly do we bridge that gap? Well, welcome to this explainer. Today, we're going to unpack the fascinating, deeply hidden mechanism that literally constructs our reality. It's called the 2.5D sketch. So here is our roadmap for today's deep dive. We'll start with 1, the illusion of depth. Then 2, Mars framework of vision. 3, decoding the 2.5D sketch. 4, visual cues and computation. 5, AI discovers 2.5D vision. And finally, 6, real-world 2.5D applications. Okay, moving right into section 1, the illusion of depth and the gap between our eyes and physical reality. In visual perception, there's this massive, fundamental hurdle that experts call the inverse optics problem. Basically, ask yourself, how do flat eyes see a 3D world? You are somehow deriving a plausible, solid, three-dimensional scene from an input that is inherently ambiguous and two-dimensional. Mathematically speaking, a flat image could represent an infinite number of 3D realities, right? It could be a tiny object up really close or a massive object miles away, and yet your brain instantly and consistently settles on the correct one. This setup perfectly illustrates the massive computational gap we're actually dealing with here. On one side, you've got the 2D retinal image, literally just flat pixels of intensity and color, with absolutely zero spatial depth. And then, on the other side, you have the fully realized 3D physical world, which exists independently of wherever you happen to be standing. To get from a flat plane to that full environment, the brain desperately needs an intermediate step. It just can't jump from flat pixels to full 3D objects in one single leap. Which brings us to section 2, Mars framework of vision and the 3 stages of sight. Back in 1982, a genuinely brilliant cognitive scientist at MIT named David Marr published a totally groundbreaking framework. He basically proposed that biological vision operates a lot like a sequential assembly line, transforming raw light into understandable shapes across 3 very distinct representational stages. It starts off with the primal sketch, then it moves into the 2.5D sketch, and it finally arrives at the complete 3D model. So before you can even recognize a coffee mug or a friend's face, your early visual system acts as this incredibly basic edge detector to create that first step, the primal sketch. It's hunting for what Marr called luminance discontinuities. That's just a fancy way of saying sudden, sharp shifts from dark to light pixels, which it uses to map out abstract boundaries. At this stage, there is absolutely no depth. It's more like a highly detailed, flat, black and white line drawing of the world. All right, section 3, decoding the 2.5D sketch from the viewer's perspective. Let's really get into the weeds here. The 2.5D sketch is entirely viewer-centered. What does that mean? Well, it doesn't know what the back of an object looks like. It is only mapping the surfaces that are facing you directly. Honestly, the absolute best way to visualize this is to think of a low-relief sculpture, kind of like the face of a coin. It's not a fully rounded 3D object that you can walk all the way around, but it does possess bumps, curves, and slants, all mapped relative to exactly where you were standing in that given moment. Now, if we look inside this 2.5D representation, it's basically a collection of complex geometric maps. First, you have depth maps, calculating relative distance. Then, you have what Marr called gauge figures. Just picture millions of tiny arrows sitting on every single inch of an object's surface, pointing outward to tell your brain the exact slant and tilt. It's surface normal. Combine those arrows with occlusion boundaries, which tell you precisely where one object is physically blocking another, and boom, you have a perfect topographic map of your immediate point of view. Let's look at how that actually happens in section 4, visual cues in computation and calculating depth. To synthesize this incredible topographic map, the early visual cortex in your brain, specifically the areas we call V1 and V2, has to do some serious heavy lifting. And it does this using 2 distinct types of cues. First, you've got binocular cues, like stereopsis. This calculates relative depth by measuring the geometric disparity between these slightly different images received by your left and right eyes. Second, we have monocular cues, which, you guessed it, require only one eye. This includes things like occlusion, texture gradients, and shape from shading. Your V2 neurons basically weigh and fuse all these cues together, prioritizing the most reliable ones to generate that incredibly robust 2.5D map. And actually, here is a truly mind-blowing detail from psychophysical research that you should take away from this. Humans are 4 to 10 times more sensitive to relative depth than they are to absolute depth. Now, what does that actually mean for us? It means your brain is highly, highly optimized for 2.5D relational processing. It cares way more about knowing that object A is closer than object B, which is, pretty vital if you're navigating a crowded room or trying to catch a baseball, than it cares about knowing the exact, isolated, metric distance of object A. So the crucial point to understand is that this whole biological process is driven by some really elegant mathematics. We can see it in this formula here used in computer stereo matching. Depth, represented by z, equals the baseline between your eyes, b, multiplied by the focal length, f, and then all of that is divided by d, the visual disparity. The math dictates a strict inverse relationship. Closer objects yield a much, much larger visual disparity. This isn't just an abstract equation. This is the precise computation required to construct a 2.5D depth map. It is literally the secret mathematical code behind our vision. This takes us to my favorite part. Section 5, AI discovers 2.5D vision and the neural network twist. So, for decades, Mars theory was strictly seen as a biological framework. But recently, researchers started looking inside the black box of modern deep neural networks that were trained on visual data. And they discovered something absolutely incredible. Without ever being explicitly programmed to do so, AI had organically evolved to replicate Mars' exact biological pipeline. We're talking low-level layers processing flat 2D data, mid-level layers developing 2.5D surface normals, and then only at the highest level layers does a fully realized 3D model finally emerge. Let's actually break down exactly how they proved this, because it's fascinating. Researchers injected what they call graphics probes into the network. You can think of these probes as translators, essentially converting the abstract math of the AI's neurons back into computer graphics that we humans can actually look at. At the bottom layers, the probes revealed completely flat planes, just 2D edges, identical to Mars' primal sketch. But in the middle layers, the AI actually started etching normal variations and shading effects into a shallow depth range. It was literally building a 2.5D viewer-centered sculpture. By the top layers, the AI had synthesized a fully view-independent 3D structure. The AI independently discovered that the absolute most computationally efficient way to understand a 3D world is to build a 2.5D sketch first. Which brings us to Section 6, Real-World 2.5D Applications, taking 2.5D from pixels to practice. Because this intermediate step isn't just theory, it actively powers the technology we use across almost every industry today. When you look at your iPhone, Apple's Face ID projects over 30,000 infrared dots to construct a 2.5D depth map of your face. It's just enough surface data to prevent spoofing by a flat photograph. Then you have animation tools like Adobe After Effects, which utilize layered depth images for parallax effects, stacking flat elements on a z-axis to mimic depth without the massive computational cost of full 3D rendering. Modern video games like Ori and the Blind Forest use this exact same parallax technique to create those stunning immersive environments. And in medicine, 2.5D deep learning models are processing MRI and CT scans right now. By integrating multi-view spatial depth cues, they can localize tumors and identify metastases far more efficiently than standard 2D analysis. And finally, Section 7, Conclusion, the convergence of mind and machine. To wrap this all up, what starts as completely flat, ambiguous light on our retina is meticulously transformed through a 2.5D low-relief sketch into a reality we can instantly interact with. And perhaps the most amazing part is that our most advanced machine learning systems have organically converged on this exact same strategy. Which leaves us with a pretty provocative thought to end on. If artificial neural networks naturally develop Mars' biological 2.5D mechanism just to be able to see a face, what other human cognitive secrets are hiding inside AI? Are these networks simply mimicking our biology, or are they revealing universal mathematical laws of perception that govern literally any mind, whether it's biological or artificial? Keep questioning what you see out there. And hey, thanks so much for joining me on this explainer.